Welcome. Let's take a look at rate of change through the lens of the speed of sound. So the speed of sound in air at 0 degrees Celsius, which is 273 degrees on the Kelvin scale, is 1087 feet per second. Experimentation has shown that the speed of sound v is a function of temperature, capital T, and is modeled by v of capital T equals 1087 times the square root of capital T over 273, where v, or the speed of sound, is measured in feet per second, and capital T is measured in kelvins. So let's take a look at finding the rate of change in the speed of the sound with respect to the temperature at temperature capital T. So as we start to think about finding the rate of change in the speed of sound, let's go ahead and use some properties of square roots. Let's go ahead and rewrite this as 1087 over the square root of temperature over the square root of 273. And we could even rewrite that as 1087 over square root 273 times t to the 1/2 power. Now this velocity speed of sound function is written in a form that's amenable to finding the derivative. So what we want to do is we want to find the derivative of the velocity of sound with respect to temperature. Now, keeping in mind our focus on rate of change and interpreting what this means, our rate of change is going to be feet per second, because we're taking the derivative of velocity with respect to temperature. So this is going to be feet per second per Kelvin are going to be our units when we're finished. So then we have 1087 over square root 273. And then the only thing to really take a derivative of is this t to the 1/2 power. And so t to the 1/2 power, its derivative is 1/2 t to the negative 1/2. So we end up with 1087 over 2 times the square root of 273 times t to the negative 1/2 power. Now, we can go ahead and bring that t into the denominator with a square root. So we could rewrite this as dv dt, d capital T, as 1087 over 2 times the square root of 273 times the square root of temperature, or we could rewrite it as 1087 over 2 times the square root of 273 times temperature, capital T. Now, so that's our derivative, that's our rate of change. This is fine with the negative exponent. This is also fine if we want to simplify it. Any of these are reasonable representations of the derivative. Now what we want to do is find and interpret the rate of change in the speed of sound with respect to temperature when t equals 273. So now we're looking at dv dt, or dv d temperature, derivative of speed of sound with respect to temperature, when temperature is 273 degrees Kelvin. Well, that will be 1087 over 2 times square root of 273 times 273. And then our units here will be feet per second per degree Kelvin. Well, notice that I've basically got 273 squared underneath a square root. So this will be 1087 over 2 times 273 feet per second per degree Kelvin. And now 2 times 273 in the denominator is 546. So the derivative of the velocity of sound with respect to temperature in degree Kelvin at 273 degrees Kelvin is 1087 over 546 feet per second per degree Kelvin. And so what we know is that the speed of sound is changing at a rate of 1087 feet per second. 1087 over 546 feet per second per degree Kelvin when the temperature is 273 degrees Kelvin. So what this means is that as the temperature rises from 273 degree Kelvin to 274 degrees Kelvin, where it increases 1 degree Kelvin, we can anticipate the speed of sound to also increase 1087 divided by 546 feet per second, which means about 2 more feet per second. I hope you find this helpful.